Swayam Prabha. Digital India. Educated India.
See these terms accordingly. So 2 zeta omega n multiplying theta dot, okay, this term will be 2 zeta omega n multiplying theta will be, now we don't have theta, we have sin theta term here, but for the low theta approximation, this sin theta is equal to theta, this is a term, this will be like a omega n square kind of a term. Okay, so that's how, like, we try to seek in wherever possible, many systems this may not be possible, to seek some kind of a normalized form of the equations, so that we can see through some of the details. For example, if zeta is found to be some value here, we know that this pendulum system is some underactuated system with this zeta value, and that speaks about its nature. So this is about dynamics. Now one can kind of do some experiments to see what is how do we get damping factor zeta. So you can think about like, okay, if I time out, okay, how much time it takes to get the amplitude to some half of its original value, something of that sort. Then one can or number of oscillations based kind of counting of change of amplitude. That kind of a thing will give you by logarithmic decrement what is this damping factor zeta. So this can be these kind of things can be carried out by studying the dynamics of the system and carrying out appropriate experiments to get the parameters. Now this is mainly again so this is like a dynamics without any input to the system, and then now if you have an input to the system, what do you consider as input? So if you think, okay, oh, I want to apply some kind of a torque on the bob or kind of a force on the bob, so in which direction you can apply the force? You can apply that needs to be in the direction of theta to have like it represented up here, or if you apply something else, what will show up here? That those kind of things we need to discuss and figure out. If you see, this is also like similar to the system that you had with the hard disk drive arm. In that arm, we had a case where the head moves on the disk. Okay, in the horizontal fashion it moves on the disk, but one can see if that disk is not there, only head is there, and at the place of the head you have a big mass attached. Then like in the vertical plane this will act as a pendulum kind of a system, and at the back side you had the coil and the magnet. Okay, that is actuator which is giving some torque on this system. That is a kind of a pendulum system that we can have. Okay, so that is one of the actuators possible in the direction of theta. But that is little bit cumbersome to create such system. So or based on like your actual practical requirements, there may be some other kind of considerations that may be coming in place for input. So we consider here that okay, pendulum is mounted on a cart, and the end of the pendulum, okay, is movable by the cart. Okay, so if you have this pendulum, okay, it is mounted on the cart, means like this point where it is hinged, that point is kind of like is moving by the cart. Okay, the cart is able to move that point. Okay, so if it is initially in motion, now I can like affect the motion by actually moving the top point. Okay, so that is how my input I am giving to the pendulum. Okay, so I am not really applying any force here, but I am just kind of moving the top point to give the input to the pendulum. Okay, that is a kind of idea. So we can consider these kind of inputs to the system, and when this input is considered here, like the hinge point motion by putting this hinge point on the cart, and then say you can say I apply force to the cart, or I can say okay, I am directly applying this displacement to the hinge of the pendulum. So these are like different ways I can define my control input. So although I have a cart here, and I can apply some force on that cart, I may choose to define that control be, let the control be input x here, or input x double dot here. Okay, so this choice of what I define to be a control input to my system has somewhat flexibility that I can have. So this is very important concept here. Okay, so I can say for the system, say there is a cart actually here for the system, but I'm ignoring the cart dynamics, and I'm saying that okay, I'm applying this control input in such a way that somehow I am able to maintain whatever desired position for the cart to be x, and I apply that as a control input to my pendulum system. Okay, so as you'll see later, for such a definition there are some good advantages that happen here. So you can see what those advantages are by saying, putting these equations together here. So this equation now with this input here, I'll not get into the details of this, how this has come, but like you can check out by using Lagrange formulation or using your simple Newtonian approach. You can simply see these terms. So you can see here, for the same system which was there previously, of course there was a damping here that we can add anyway. For that, this x double dot term appears here. Okay, so this x double dot upon L, entire of this term, okay, is some input which is in the direction of the generalized coordinate theta, because this is a theta equation, theta generalized coordinate equation. Okay, so by doing this kind of a input to my system, I get a term for my control which is directly in the direction of theta, as if I am giving a torque on this string. So normally giving a torque on the string is not possible, but because I am able to apply this desired acceleration, it is as if I am giving a torque to the string in the direction of theta. Okay, and then this helps us to develop a nice controllers later. So with this term, considered as acceleration is considered to be an input to the system, and further the damping is considered in the system, you get now this kind of a equation. Okay, so this is now simple spring mass system. You can see the second order spring mass system with some kind of a force, external force applied on this system. And with this force, now I can define a control problem that, okay, develop this u in such a way that this theta goes to 0, or initially oscillating kind of a pendulum, theta goes to 0 in some given amount of time. Okay, normally the pendulum is going to take a lot of time, a lot of oscillations it will carry out, and after some oscillation it will stop. Okay, anyway, but I want to kind of go to the final point in a very short amount of time, and how do I carry out that job? Okay, so where is this kind of utility of such systems? Just one thing comes to my mind. Where we have these overhead cranes. Okay, they are carrying some big amount of chunk of mass from one place to another place, which is hanging out of the string, and there is a cart which is on the top of the overhead crane. You might have seen these construction cranes, they have these. So you don't want this mass which is with a long string attached, and it can, by the wind, it can kind of oscillate, it can have some kind of a motion possible. We don't want that motion to happen. Its oscillation should be damped down. Okay, otherwise it may be dangerous for the personal or life. So in that case, this control could be kind of very useful. So what we do here is now for such a pendulum kind of a system, we demand that, okay, we don't want any oscillation, or if there are any oscillation, they should get damped down very fast. So how do we do that now? So this is our control and control problem defined, and suppose we find such an input, okay, u, then how do we drive the cart such that this u is applied to pendulum? Okay, that means we need to satisfy this equation. So u is there, and then x desired. Now this is not x here, x desired, we can make it as x desired here. So my x desired double dot should be that u, and I integrate this u twice, okay, with scaling factor L, then I'll be getting actually the x desired as a function of time trajectory. Okay, and that x desired, if I go along that trajectory x desired, then I'm guaranteed to apply this u that was desired here. So u itself, if you see, will be a function of time, as we propose some kind of a controller which will be a function of this theta, which is in turn the function of time, and then you integrate that twice to get x, and that x is what I'll say, okay, my hinge of the pendulum will be moved along that x. That is how I can plan my whole control implementation. Okay, So so from control design we'll get U, and we would like our x double dot to match these. So we consider trajectory to have the same x double dot, so this xt double dot. Okay, then we find xt double dot. Okay, from that xt double dot is equal to something by twice integration of U. I am missing the scaling factors here. You can put those scaling factors. Okay, so now we can, like, control force F. Suppose there is a cart pendulum, cart also is there in addition. Then I can kind of use this force on the cart to be F. By some means we can apply that force by, say, PID controller to track the trajectory which is coming out of this equation. Okay, that kind of idea can be possible for implementation. There are quite a bit of advantages of this kind of implementation, which we will not discuss for now here. But later on, maybe, if you are interested, I'll kind of show very good advantages of such an implementation, rather than considering directly this force to be my input and considering my force applied on the cart, and cart in turn is having a pendulum. Okay, so there is a cart here and the force F is on the cart, and cart in turn is carrying this pendulum along. So that is not a very great practically good strategy to implement, because there will be a friction between the cart and its wheels and other places. Okay, its sliding part. Okay, so this is a kind of a way we implement this. We propose to do this kind of a control. Okay, so this is a discussion about why F is not directly designed and implemented, because of this friction that is there in the systems anyway. Okay, so you can do some kind of equations development of what will happen in the presence of friction, how I consider control with friction in the case of cart pendulum system, and then, like, things will unfold a little bit what I am saying here. So the friction is major culprit to faithfully implement F that will make my control better. Okay, I can tell you something physically here. Okay, see, if the friction had not been there, then any pendulum motion here, okay, if the pendulum motion happens here, and if there is a cart without friction, that is, there some mass is there, of course, then the cart would respond to the motion of this pendulum. As a reaction forces there acting on the cart at this point will start moving the cart here and there. And imagine the worst possible case, when the friction is so high that it cannot move at all. Then even if, like, the motion happens here, the cart is not moving. So if the cart is not moving at all, then, like, your feedback is somehow lost there. Like, this so you cannot affect pendulum, or pendulum is not able to affect the motion of the cart in some way. Okay, and that is a big hurdle for getting any kind of a feedback based on this force implemented faithfully. Okay, that much I can tell you as a physics part, but to really get to this, you will need to write the equations in the form of this pendulum cart total system. So that will be 2 degree of freedom system, the cart degree of freedom and the pendulum degree of freedom theta, and the force considered as an input. So single input but 2 output kind of a system will be there. And with the approach that we are discussing here right now, those all complications of, like, under actuation will be gone here if I consider U to be this kind of input, and I implement this U by using this double integration and say some kind of a PID controller. Now there are some kind of a mathematical questions that one may pose, that okay, how do you guarantee that we will be able to track this xt trajectory very well by using some PID controller? Okay, those kind of more kind of finer mathematical aspects would be there, which we are not. I mean, we say that okay, our PID controller is fast enough to do that control so that it is able to kind of follow the desired trajectory in a very appropriate sense. Okay, so this is what is this discussion about this force here. Okay, so we come back to the system now. In this standard form, it looks like this, and then we can say write a transfer function of it, and then see the open loop poles are here. Then now we can propose some controller to move these poles around and things like that. Okay, so that those all kind of things can be done now. So we propose a PD control or P control, or all these kind of different controllers can be done. Some discussion that you can find here. It is pretty simple to follow through. So the control problem is defined to have some say we just want to settle down faster than what it is its natural damping would allow it to do. So we may propose like the derivative control, or like complete proportional plus derivative kind of a control to achieve the task. Here we have two parameters available for us to tune, and so we are now seeing entire thing, all this development only in the differential equation kind of a domain. Okay, so you see we have chosen to do this. It's up to you to kind of consider that. Okay, if you want to kind of do it on the Laplace domain, you can do that and see, okay, now for the new pole locations, what should be these KD and KP gains, so that I can move my poles to appropriate location based on choice of KD and KP. So this is the final form of an equation in the differential equation domain. See, this is an error equation because theta itself is our error, because we don't want theta, we want theta to get damped out. So theta should be desired to be 0, then like the error equation is same as the equation in theta. And with this we can now plan, like what we want, how fast we want. We choose omega nu based on that. And so this is our omega nu here, omega nu square, and this is our nu 2 zeta omega n complete term. So we have some kind of a choice in both the cases to affect, and we can choose these gains to kind of have whatever desired omega nu and zeta nu, and based on that our system response will evolve. So you can use the standard system second order system specifications to design these values, and like your problem will be solved here. Okay, and once we get this zeta, then your u, I mean zeta and this your Kp and Kd are sized appropriately, then this is final u, and then you can get this no, this is with the theta d is equal to some value, but so you get the u in this form here, and then implement it by like taking double integration of this and mapping it to x desired, and now x desired is like my motion of my hand here. Okay, so if you see here, let me change this view. So I have this pendulum bob here. You can see I'll use a shorter length. So with this, if it is initially in motion and I want to stop this motion, I need to kind of move such that it stops immediately. Otherwise, it will continue a lot of oscillations to move. I move this my hand in such a way that it gets to the stop condition very fast. So I'm doing something in my head to do that. You can also try out, and you will be able to also do. So whatever is happening in my head, okay, in some way is getting captured in the mathematics that you see on the slides. Okay, so I can kind of move this quickly to do the job. So I'll not be able to do as quickly as, for example, these equations can do for a tuned gains. Okay, so that is the beauty of using the mathematics to some kind of a nice way developing control over such a kind of a phenomena. Okay, in one of the examples. Okay, there are many such examples one can kind of start developing and do that, and this has immediate practical applications in overhead cranes, kind of a cart that moves in overhead cranes. Okay, so let's move on from here to the other example. So you can get to more details. If theta desired was not 0, then like we have some difficulties here. Okay, so now one can see this whole in the Laplace domain, how things will be represented, and with this one can kind of see, okay, this feedback, some kind of a unity feedback here with Kp Kds here. Then you can, as we have discussed, one can do root locus analysis of such a system. Okay, and that also kind of helps to kind of tune the gains or see the things in a different kind of a approach. Okay, so this is another example about the simple PD control for regulation purpose. So this is much simpler form which we have already seen. So it's just again PD control applied here, and you can see this in the error form here. Okay, so the idea here, if you see from this error dynamics, what happens is that there is a virtual spring, as if virtual spring is attached to this mass, which will have equilibrium at the desired reference position. Okay, that's what is. So one can interpret this control as if we are actually attaching some virtual springs and damper to the system. Okay, to get some kind of a physical insight into. Okay. So this is the same kind of a discussion a little bit in the domain of this example. Now when we introduce this integral part, okay, whenever we have the steady state error not going to 0, that time we introduce this integral part. So you have seen in your simulation of the simple single link attached to motor kind of a system, that when you try to oscillate this pendulum, it doesn't kind of come to the vertical position because of the friction. Okay, the friction is what is not allowing it to settle into desired position or in the vertical position. Okay, so this friction is causing some kind of a steady state error in the system. Okay, and even if this system is to move in the horizontal plane, okay, the same things would happen as would happen for this mass which is in the horizontal plane without the spring and damper kind of a case. Okay, so these are, anyway, the spring and damper are actually the virtual springs and damper that are put in the system. Okay, so if in the presence of these virtual dampers in the system, one can see that if I keep this mass oscillating, it will stop at some point which is not really matching this R completely in the case when there is a friction. Okay, so friction in the system will not allow it to reach R. It will have some finite error that will be there in the system. That is a kind of a point. So in the case of that kind of a error, then you introduce this integral control action. Okay, when the system has this steady state error. Okay, you see the response to the PD controller, and you see that, okay, there is some kind of a steady state error, then you introduce the integral control action. Okay, so we will talk about this integral control action part I think this main kind of a thing, or maybe we can give a summary of like when to use these different kind of control actions in general in the system. So this will be good to kind of know. And then as we have seen, like we use this make use of this standard first and second order system responses which we have seen already. I'm just flashing the same slides here actually. So these are the standard first and second order system responses with this information should be handy to us for application in several cases. And then we'll have this formulae for the second order system behavior formulae. Okay, for maximum overshoot, settling time. This should be also handy to you. Okay, so that as we saw in the pendulum problem, for example, we can use them to set up like these omega n and zeta to have a desired value, or when you do the pole placement problem, the two dominant poles which you are placing close to the imaginary axis, they can have some values taken by this thing. Okay, so these are the typical parameters that we define. Okay, so this is a formula that is given in the slides. You can just go through them to make use of them in the pole placement problem or in simple second order system problem. Okay, these are some of the general guidelines that one should be aware about. That proportional control action will typically make the response faster, increase the overshoot, and increase the settling time. Okay, so if you use this Kp gain higher and higher, it amounts to increasing the settling time also. Okay, although the response is faster, it will settling time also increases. So for the settling time to decrease, we will use the Kd gain. Okay, so this derivative action decreases the overshoot and decreases also the settling time, and but the response is a little bit sluggish. Okay, so the combination of Kp and Kd would give you some kind of a nice response possibility. And integral control action, again, it makes the response faster. It actually introduces some zero close to the origin in the controller transfer function. Okay, not really for the system thing, but controller transfer function will have a zero. Okay, so it may amount to have a zero in the system also, but we don't know. It depends upon the kind of a form of a system in the closed loop. Okay, so it makes the response faster, increases the overshoot and settling time, but it takes care of the steady state error. Okay, so imagine if you have a steady state error like this here, and integral control action is there, derivative because theta dot is 0, derivative control action is stopped. Proportional control action, this theta is constant, so proportional control action will still keep going, but it is not changing. Okay, Kp times this error will be a fixed kind of amount of input that will be going into system, but that input is doing nothing to the system, because say for friction, for example, like even if you apply a force, the system is not moving. That kind of a case will happen here. So in this case, the integral control action will help, because if you put an integral control action, if you see from this point, just like if the integral is starting from this point, you can see the integral control action will be the area under this error curve. So area between these two lines will be the integral control action. That area will keep on building up. At some point, like it will exceed the friction value, and depending upon gain that you have used, and this error will be taken care of. So there is a chance that with this integral control action in the presence of friction, this build up happens so quickly that with sudden application of that force, the system moves on the other side. Okay, and again there this integral control action will have to come in picture to move it further back, and there are certain zones for this process that system will keep on hunting between the two values rather than settling into some final value. Okay, so one needs to be careful about choice of the integral gain to prevent this hunting. Okay, so how that is to be avoided, and those kind of things are like more kind of a mathematics can be worked out for such a kind of a case. Okay, by considering say your friction model, or there are many other techniques also available. So you use this friction model, and use something called describing function method to come to what is the frequency that your system will be keep hunting into. So that these are not the matters of our discussion here, but one can use these methods for such phenomena if at all you find somewhere in your future application of control this thing is happening. Okay, so this integral control action can have a possibility of system getting into hunting. Okay, and how do you tune this PID gains typically is given in this procedure called Ziegler-Nicholas procedure. It's just a matter of some kind of a steps that you follow. You can see these more details at this. There's no point in getting into and explaining those steps. I mean, it's simple information. You just kind of follow the steps and your gains will be tuned. Okay, so you do look at this for practical tuning of this. It is based on only like the experimental system is ready and I'm now going to tune the gains, or your simulation system is ready and I'm going to tune the gains. This is a way you can tune the gains. You can try it out on some of the systems that we are discussing as a part of assignment in the class. Okay, so this is, I think we'll stop here for this discussion, and these implementation aspects we have already covered some of them, and there are some more issues listed here. Okay, sampling time we have seen already, then effect on system due to sampling we are yet to see, then filters, these are all related to your sampling, and then speed of computation, or how much is the computation that we need to do. That is also important consideration, that we should finish computation of control within the sampling time, and speed of various interfaces also is a matter of things, action that has to be completed within the sampling time. Okay, and so these are many, some of the aspects we have seen, we have not, so but you should have this list to see or check or put like a check mark. Okay, you have taken this aspect into consideration. This is a kind of a checklist you can do for controller implementation. You have considered all these aspects or not, you can check that. Okay, so maybe we will stop here for now,